Training a neural network without visualization is like flying blind. You can watch terminal text scroll by for hours, but to truly understand what your model is learning, you need a control center to translate those raw numbers into visual insights. In this video, we'll build a comprehensive tracking suite natively in PyTorch. We will capture scalars, images, distributions, high-dimensional embeddings, and structural graphs, all in one place. To follow along step by step, you'll need an active Python environment equipped with both PyTorch and TensorBoard. Visualizing your training metrics is the fastest, most reliable method to debug failure points. It also provides the concrete evidence required to prove your model's efficacy to stakeholders. Step 1 is establishing the base pipeline. We start by loading the TensorBoard extension directly inside your Jupyter or Colab notebook environment. Running the magic command %tensorboard-logdir equals logs initializes the dashboard. Setting this root storage directory tells TensorBoard exactly where to look for your incoming data. It is crucial to launch the dashboard before you log any data. This ensures the interface captures and displays your real-time updates as the model trains, rather than requiring a manual refresh later. To actually send data to that dashboard, we import the SummaryWriter class from torch.utils.tensorboard. SummaryWriter acts as a central hub. It ingests the raw outputs from your PyTorch model and distributes them directly into your structured log directory. Setting up this pipeline correctly prevents data loss. It also automatically organizes complex, multi-experiment runs into separate folders, keeping your workspace clean. To track single performance metrics like loss or accuracy across iterations, we use the add_scalar method. If you want to group related metrics, such as comparing your training scores against your validation scores on the same graph, you use the plural add_scalars method and pass in a dictionary payload. This chart shows metric evolution over 50 epochs. We can easily compare training and validation curves side by side. Notice the divergence between the lines. On the lower graph, the blue validation curve flattens entirely, while the red training curve continues rising. Instantly seeing the scalar divergence empowers you to diagnose overfitting or underfitting the moment it happens, saving you hours of wasted compute time. Beyond single numbers, we can move into visual debugging by logging validation outputs with the add_image method. When passing images, you must include the argument dataFormatsHWC. This tells TensorBoard to read the dimensions as height, width, and channels, flattening the data correctly into a recognizable preview. Next, we use the add_histogram method. This tracks how model parameters and weights shift and spread out across different epochs. This histogram shows the weight distribution of a standard, unregularized model. You can clearly see a wide, jagged spread of values pushing far outward. Now look at this teal histogram for a regularized model. The distribution is much narrower and tightly constrained near zero. Histograms act as a diagnostic X-ray for neural network health. They reveal systemic issues like vanishing gradients early, before they ruin an entire run. To evaluate a classifier's confidence thresholds, we rely on the add_PR_curve method. This graph shows the inverse relationship between precision on the y-axis and recall on the x-axis. Notice the sharp drop-off point for the ankle-boot class, which marks the exact threshold where model confidence fails. For high-dimensional data, the add_embedding method visualizes clustering. You provide a matrix of your feature vectors and pair it with a metadata list of labels so the points are correctly identified in space. This visualization projects that high-dimensional data into a navigable 3D point cloud. You can verify visually that the model is grouping similar clothing features closely together. Finally, the add_graph method takes your written Python class architecture and translates it into an interactive visual node graph. These advanced tools translate high-dimensional tensors and weight updates into human-readable insights necessary for fine-tuning. We now have a fully realized TensorBoard environment that nests seamlessly inside your active workflow. We have established a comprehensive suite of tracking tools: scalars, images, histograms, precision recall curves, embeddings, and full architecture graphs. The result is granular oversight of your training and validation runs, bringing diverse data streams together into one accessible dashboard. Mastering TensorBoard elevates a practitioner from simply executing code to actively observing, understanding, and steering the training process.